Oh, wait, Tiffany's coming in. All right, I think we're all in here now. So yeah, like Kaushik said, today we're going to be going over some code samples. So yeah, just get ready for that on your computer. But yeah, since we didn't get to go into linear regression last time, that's what's going to be this week's topic. And so yeah, we're just going to have an in-depth look into how linear regression works, and then derive some equations specifically for ordinary least squares, and how that works. And then we're going to implement it using code with Python specifically. And so, yeah, Kaushik, you take this part.
Yes, like you said, we're just going over linear regression. Specifically with linear regression, we're going to go over these 4 topics: multivariate, multiple linear regression, and then we're going to go over 2 types of, I think, regularization, L1 and L2. Unless I said that wrong, but and then after that, we're going to go through an actual. We're going to code a type of linear regression model, ordinary least squares, and we're going to go through the code. So for that, we're going to actually set you up with the environment, and we're going to write our code in Jupyter Notebook. If you don't know what that is, it's just like it's a way to write and execute your code one by one, but like line by line, but like actually, write code in the middle of your execution, if that makes any sense. Yeah. It'll make more sense when we do it.
So yeah, yeah, let's just get started. And so so to get started, like we said, I think it was in the second meeting where we were explaining the differences between regression and classification. Linear regression is a regression model. So it takes in a numerical input and it tries to give a numerical output. And specifically, we're going to be looking at least squares algorithms, although that's not the only linear regression algorithm out there. But this is the one that I was talking about, where if you have the error is basically calculated by the difference between the actual data point and the predicted squared. And so that's what all these methods are based off of. And so the first one is ordinary least squares. And so this is like the most basic version to perform simple linear regression on. And it's just like the standard simple version. It's pretty effective for simple correlations in data and finding patterns. But there are some things to take into account that sometimes might not be able to that might cause ordinary least squares to perform badly. And these 2 things are specifically, one of them is heteroscedasticity. And so let me pull up Paint. So the scedasticity of a data set here is basically how much variance there is in the data points. And so if you have a data set, let me like draw an example one here. Something like this. So this data set right here, if you had this, it would be considered homoscedastic, because the scedasticity, or the variance from the mean for the entire data, is very similar. Right, so if you were to draw a line of best fit here, right, the error bars for each of these points would be be pretty close together. It'd be pretty similar. At the same time, if you had something like this would also be considered homoscedastic, because like I said, the spread of the data is still similar to how it was before, right? So now the whole data is, it's all spread out further away. But that's homoscedasticity. But when you have heteroscedasticity, that's when your data has different levels of spread. And so that's what you see in this example image right here on the right side. So you see how it starts out like very close together, not spread at all. And as the data continues on, it gets a lot more spread apart. And this can happen with real, if you record real life data from real sources, this can happen due to different factors. But the important thing to consider is that this is bad for ordinary least squares. And yeah, ordinary least squares doesn't perform particularly well with these when you have this type of data. And so for this, you might want to consider instead using weighted least squares, which is pretty similar to ordinary least squares. Um, but it just adds like weights onto the. I'm not sure how to like explain this simply. Um, it just adds weights onto the error terms, right? And then the other thing to take into consideration about your data when you're trying to use linear regression is sometimes there may be correlations in your error. And so this is what the example down here, the bottom right shows. All right, you can see there's certain points in the data where there's a lot of error. And you know this may be correlated, right? If you observe in real life, oh, this particular spike right here is caused by a certain phenomenon, and this other spike is caused by something else, right? That would be correlated error, correlations in the error terms. And for that, you'd use generalized least squares, which is an even more like robust model than weighted least squares. And so another regression algorithm you could also go over is called maximum likelihood estimation. And it's basically, it works differently from least squares because it basically looks at it as a probability distribution. We're not going to go to that. We're not going to go in depth into this one. So don't worry too much about it. We're mainly going to go over OLS here. And then the other two are multiple linear regression and multivariate linear regression. And so multiple linear regression is whenever you have more than one like input variable, right? So here we'd have just simple linear regression, which is one input numerical value and one output numerical value. But what multiple linear regression does is it can take multiple, like however many dimensions you want for your input, right? So rather than just taking, you know, just one feature of your data set, you can take like 4 other things into account. And multivariate linear regression, on the other hand, is when you have multiple output variables. And this in and of itself is not really like a different machine learning algorithm than regular linear regression, because this is essentially just running multiple linear regression models on however many output variables you have. Right, so this is basically just doing linear regression multiple times. And yeah, so now we're gonna go over ordinary least squares. So I already have this open. Actually, let me pull up a poll here, because this does require some concepts in math that some of you may not be familiar with. Let me see. Yeah, so the poll is just going to be like a couple of concepts in math, and just like yes or no for whether you're familiar with it or not. Let me see. Question. Actually, it's not too much. Yeah, I think this is going to be it. Let me see if I can launch this. Wait, do you see this poll?
Yeah.
Oh, okay. So yeah, just indicate whether or not you're familiar with these things, because these are going to be concepts we're going to be using from OLS. Oh, oh wait, I think I forgot to include a couple of other things there too. Shouldn't be too important though, but they're basically just matrices and vectors. But yeah, I'll go over those two anyways, since I forgot them on the poll. I'll just cover them quickly. Okay, 6 out of 8, I think is enough. I think everybody here is familiar with what a derivative is, so we're not going to go over that. But yeah, we'll go over matrices, vectors, summation, partial derivative. Okay, so let's start with summation because it's the simplest. And so yeah, this is basically the notation for denoting when you have a sum. And so it's a symbol right here. Oh, that's not very well drawn. There. Right, and so this, the sigma symbol basically denotes a sum of numbers. So if you start with I equals 1, 5, right? This basically iterates from I equals 1 all the way to 5. And so if your expression here, you have 1, or not 1, sorry, I, right? This is equivalent to saying, you know, I equals 1, I equals 2, I equals 3, I equals 4, and I equals 5. And if you have, instead of just I as your expression, say you have something like I squared, right? This would be equivalent to saying 1 squared plus 2 squared plus 3 squared, etc., etc. Right? All the way until you reach the term on top here, right? So yeah, this just iterates through the I terms from the bottom to the top, right? 1 to 5, and adds up all the resultant expressions here. Okay, and then next thing is partial derivative. Okay, this one's a little more complicated. But essentially what it is it's basically taking derivative with respect to only one variable. So you know normal derivative, right? You have f of x equals x squared, right? X is sorry, not x. F is a function of only one variable here of x. And so, you know, taking the derivative is easy because you only have one variable to consider, which is x, right? So f prime of x would be 2x. However, when you have multiple variables in your inputs, so x, y, right? Then you can do something that's called a partial derivative. So say that your fxy is like x squared y, right? So you input an x value, you input in a y value, and you perform this, and that's what the output of fxy gives you, right? So here you can perform a partial derivative with respect to either of these two variables. So if we do it with x, so the normal derivative notation would be like this, right? df dx. Right, but when you have partial derivatives, instead you use a different, so I think this is lowercase delta. And so now we're using the fxy here. Oh, Joaquin's into the waiting room. Right, so instead it looks very similar to the normal derivative notation, except here you can pick either to do x or y. And that determines which variable you're doing the derivation with respect to. Right, so let's pick x. Right, so what would this be? Well, the way to perform a partial derivative is pretty simple. It's the same thing as a normal derivative, where you take it with respect to the bottom variable when you're taking respect to, and you keep all the other variables. You consider them constants, right? So imagine this y was like a 5 instead, right? This would be 5x squared, and so the derivative of that would be 10x. And so, but in reality, you know, this is a y, but you consider it a constant, right? So yx squared. So the partial derivative of this would be not y, 2yx. And then you can do the same thing for y. And so if you had partial derivative of f with respect to y, right? You instead take the derivative with respect to y and consider the x squared a constant. And so if x squared, again, you replace that with 5, right? 5y, the derivative of this would just be 5. You can consider the x squared in the same way, right? So x squared y, right? The partial derivative with respect to y of this is just x squared. And that's pretty much all you need to know for partial derivatives for what we're using them today, what we're using them for today. Okay, the next thing, matrices and vectors. And so matrices, we're not really going to use them in this, in our math derivation. It is going to be included as part of it, but it's not really important. It's just a way to express it in like a much simpler, easier way. Right, so if you have like a matrix is essentially like a 2D array of numbers, right? Where you have like 5, 1, 2, blah blah blah, right? And then a vector is essentially a matrix with only one row, one column, right? So this is a matrix, and a vector would just be like whatever number is here, right? And if you think about it in terms of if you've had physics before, or some other class where vectors are more like arrows with the magnitude and direction, and then in math you can think about it as like this being the x term, this being the y term, and this being the z term. So each row of the vector denotes a dimension. And so yeah, that's pretty much a quick math review. So yeah, let's get into it here. All right, so oh wait, somebody's talking in chat. Okay, yeah, let me finish this math first, Kaushik. So yeah, basically consider that you have a data set. You have these data points, and these data points, let's say the x axis is like say it's like price of eggs, or say like yeah, x axis is how much you pay, and y axis is how many eggs you get, right? Say like you're buying eggs at a supermarket and you're making this graph, right? So this point would be like oh, you paid $2, right, and you got 1 egg, right? And this point right here would be like, oh, you paid $5 and you got 3 eggs, right? And so this would be the x and y. And so when we're finding a line of best fit, right? So first of all, how would you define each of these points, right? So you have all your x variables and your y variables, and so you'd have, let's see. So this point would be like 1, 1, right? This one would be like 2, 1. This one would be 2, 2, etc. Right? This is how you'd represent it in like mathematically, right? The points. But instead, what we're gonna do here is instead of denoting them one by one, we're gonna denote them by I, right? And so this first one would be like, right, I equals 0. The second one would be I equals 1. Third one would be I equals 2. Actually, no, I'm thinking 2 computer science. This would be 1. 2, I equals 3. Right, so our x1, right, so it'd be the x term of the first point here. So it'd be 1. And our y1, right, same thing here, the y term of our first point, 1. And so we can define the same thing here, 2, y2 equals 1, etc. And so that's how we're going to denote these. And so Yeah, now back onto the main question. So if we're trying to create a line, right? So say we have a line here. Oh, wrong color. Like this, right? So how would we be able to know where these points are in terms of the line, right? Not in terms of x and y, but relative to the line. So as you probably know, lines are usually in the form of y equals mx plus b. But here, instead of just doing mx plus b, we're going to denote it y equals beta naught. Oh, sorry, this is backwards. Beta 1x plus beta naught. Okay, so the beta naught would be like your y-intercept. So it'd be, if you extended this all the way down, right, it'd be like your y-intercept here. And your beta 1 would be your slope. Okay? And so this would be the equation for your line that you're creating. And so if you're trying to predict, let's say like x equals your x2, right? So say like this is remember how we denoted them by I equals 1, I equals 2? So if this is I equals 1 and this is I equals 2, then your model's prediction for I equals 2 for the second point would be y2 equals, it looks more like a z, equals beta 1 times x2 plus beta naught. Right, and this is what this is essentially doing is plugging in the x value of this, I equals 2 points, and getting what the line's value at that point. And so say like x equals 2, you plug this into here, and your y gives you this point right here. Right, so this would be your y2. And then you can do the same thing for all the other ones. So for your y1, you do y1 equals beta 1 x1 plus beta naught. Right, and so that's just, like I said, again, plugging in the x of this value, getting this y coordinate. This is your y1. And so now we have the predictions, right? These are what the line predicts to be those values. And so now how do we express the points in terms of, the line of those predictions? Well, as you can see, for each term, there's an error. So I'm going to draw this in green. Like for y1, for example, right? You predicted beta 1 x1 plus beta naught, and it gives you this value right here. The error would be this entire thing. The distance between the actual one term and the y1 term. And so, for your y2, that'd be your error 1, right? Your first error for your first point. And so, wait, let me put this back. Yeah, so your first point, it's comprised of this error and this line. So now we can actually express this point in terms of the line and an error. So now I can say that, this would be the prediction. And so all we have to do to this is add an error term. Plus error, error 1, right? And this error 1, like I said, is the same thing. It denotes the error term for the I equals 1 value here. And then we can do the same thing for here. So this is currently the prediction equation for the second point. So now we can extend that, add the error term here. And that's essentially adding this onto the predicted line and getting to this point. Right? And so you can see that for any point for yi, right, you can express it as beta 1 xi plus beta naught plus the error term. And this is how we express each each point here, each y value, in terms of the line and an error. So right, for this particular y value, you take the line prediction, so beta naught 1, beta 1 xi plus beta naught would give us this point right here, plus the error term for that one, which is this. Right, you add those two together, and you get this point, right? You get the actual point. And so, since we have this equation for getting each point in terms of a line and an error term. And so now we can define our entire data set that way. Actually, wait, let me put this back. Right. So, right, here you go. So, we can define our y2, blah, blah, blah. And then we get to our yi, right? Until we get all the way down to our yn. And n here denotes the total number of points in our data set. Right, so yi stands for a specific index, so a specific point of the data set. Yn is a total number of points. N is a total number of points. So that means yn is the last point in the data set. Right, equals beta 1 xn plus beta naught plus error n. Right, and so we can express all of our points this way. But you can, not all of our points, all of our points are y terms here. But we can put this into a vector. So if you remember, a vector is just a one column matrix, right? We have numbers, right? And so we can define a vector here where our y, I don't know what this is called, like y arrow or whatever, our y vector, right, is this expression for every single y. Right, so we get our, our y1 would be this, x1 plus beta naught plus error term. And then, our next one would be the same thing except for x2 and error 2. And, we just continue this until we reach all of our points. And this would be the vector of all the y values for every single point here. I'm going to draw another paint window here. This is too much to keep tracking this one now. All right, so now we can, we can define our y vector here. Oh, oops, this is too small. All right, our y vector. And if you go back to this one, okay, I'm not sure how many of you know what matrix multiplication is. But yeah, I don't think we have time to explain how matrix multiplication works. So I'm just going to write the simplified version here, where we have, where is it? Y equals, here it is. A B vector plus error vector, right? And so, yeah, like I said, this requires knowledge of matrix multiplication. But basically, think of this y vector as, all the y values of the data set. Think of this A vector as the slope and the intercept. Sorry, not the slope and the intercept. All the x values for every vector. In reality, this A vector looks like this. It's 1, 1. It's 1, 1. It's just a 2-column vector with 1 and then x1, x2, xn. Right, this is what the A vector looks like. And then the B vector is your slope and y-intercept. Right, and if you want to take a screenshot, if you know how matrix multiplication works, and figure out why this works the way it does, and also your epsilon not your epsilon, your error vector is just all your error terms. And right. And yeah, if you know how matrix multiplication works and you wanna take a screenshot and work this out for yourself, you can. Right. And so the reason, right, this particular notation isn't too helpful here because we're only dealing with ordinary least squares. But when you write it out this way, and like y vector is equal to a vector plus the beta vector plus the error vector, or sorry, a matrix. When you write it out in this way, it makes it easier to generalize to other forms of regression, such as weighted least squares and generalized least squares. But since we're not going to go over that here, we're just going to leave it at that, and we're going to go back to writing it in a more familiar format. For those who don't know, who aren't too familiar with what matrices and vectors look like, right? And one last thing here, we have y, y vectors is equal to this, so naturally, we could just do a simple algebraic maneuver where we have the error terms is equal to the y vector minus a beta. Oops, that's right. And so, yeah, like I said, this is just simple algebraic manipulation where we're defining what our error terms are in terms of the y values of the data set and our predictions, right? And so now, one last thing you're going to want to know here is what the norm of a vector is. And so, write this out. Because this is what we're going to use for our error. So our error term here, or what the least squared error, what we're going to try and optimize is this. And what are these double bars? Well, the norm of a vector is essentially the Euclidean distance from a zero a zero vector to whatever vector you're getting the norm of. So if you have how to take the distance of like an x and y value, right? You have x and y, right? You're trying to find the distance between 0 and xy, right? You have the equation a squared plus b squared equals c squared, right? And so to solve for c, the distance, you just get square root of a squared plus b squared, right? And that's what you can do in 2 dimensions. And so the norm of the vector is essentially the generalization of that, where the norm of this error vector is essentially the square root of the first error term squared plus the second error term squared plus the third error term squared, etc. Whoops, yeah. All the way into our last one, squared, right? And so this is what the norm of the vector is. And so this is what we're trying to minimize here. Because if you think about it, this is what the least squared equation is, right? So if you remember from that one lesson, right? Or if we have these data points, right? And this is our line, right? So our error terms, which are these green lines, right? So the mean squared error is just all of the error terms squared, right? So this squared plus this squared plus this squared plus this squared plus this squared, right? And so the norm of that is just all that except with the square root. And so this is what we're trying to minimize here. And so what we can do here is do the norm operation on both sides of this vector. Right, so we can do the norm of the error vector is equal to, I'm going to need to extend this out, is equal to the norm of the y vector minus the prediction. right? And so now, right, now we have our error function here. This is our error function, right? So this is what we're trying to minimize here, trying to minimize the error. And so how can we minimize the error function? Well, there's two ways. Because we have our line, right? We have a line of best fit. And if we have just this linear line here, then what two variables do we have control over in this line? Well, we have control over the slope and the y-intercept, aka beta 1 and beta 0, or beta naught, right? And so those are the two terms we're going to be using to optimize this function. And so what our goal here with the ordinary least squares is to minimize with respect to beta naught and beta 1, right? Our error terms, right? And so when we put this into practice, we actually square the norm for both sides here. So in practice, our error term actually ends up being this squared, right? And so if you go back here and look at the definition for the norm, right? If you take the square root of all these squareds, all the squared error terms, right? And then you square this whole thing, right? This just cancels out the square root. So you just end up with all the error terms added up together. So, minimizing this is equivalent to minimizing with respect to beta naught, beta 1, our minus a, right? Because we're just performing this minimization and squared function on both sides of this equation. Okay, let me open up a new paint. All right, and so now we're going to go back to writing this instead of as vectors as sums, right? Because remember, this epsilon vector norm squared, or this error vector norm squared, right? It's just the error terms squared all added up together. So now we're going to rewrite it as, whoops, too small. Minimizing one, right? The sum, right, from I to n. Oh, I equals 1 actually. Of, right, here we have, this would be all the y terms. So yi. And then this would be a prediction. And if you remember a prediction function, it was just this, right? Ignoring the error term, it's just this, right? It's just plugging in x into the slope and seeing what the y of the slope, y of the line gives you, right? And so here, so I think I copied here. So then, right, minus our prediction, which would be minus beta naught minus beta 1 x1 or xi. Right, so this would be, so this is the actual term and this is the predicted term. Oops, this is the predicted term. And so this is, if you think about it graphically, it makes sense, right? So if you have a term right here and your line is here, then you're just getting this y value minus the predicted y value, which is here. Right? And what do you get when you subtract this from this? Well, you end up with the difference between them, or the error term. Right? And so that's how that makes sense graphically. And so, the last step we have left for this is to square it. Right? And so this is the same thing that we had before. We're minimizing with vectors and matrices, except we have it in the form of a sum now. And so yeah, we just write it this way because it's a lot simpler and easier to understand. And so now we're just going to rewrite this as our error function, right? So this whole thing, right, which is the sum of all the error terms squared, we're going to try to minimize that. So minimizing beta 1 of capital E, right? And this is just our function for errors. Beta naught and beta 1, right? And so this is just rewriting this, right, where E is equal to, this, right, where you plug in a beta naught and you plug in a beta 1, which if you remember is a slope and a y-intercept, right, plugging those in and then getting the error value, right? And so what does this mean? Well, this is, like we said, this is the error value, and we're trying to minimize it by modifying beta 0, beta naught, and beta 1, right? We're essentially trying to find the slope and the y-intercept values that give us the least error, which is what we want with ordinary least squares, right? That's our final goal. And so now I'm going to introduce two equations here. And so for our first one here, right, it's going to be the partial derivative of E with respect to beta naught. And the second one is going to be partial derivative of E with respect to, beta 1. Right, and if you remember from earlier, this is getting the derivative of E with respect to each variable. Right, so, doing it in this case, right, would be having to derive or get the derivative of E considering only beta naught, right? Consider any beta 1s in this, in the derivation as constants, right? And so since we're only taking, like I said, derivative with respect to beta naught, everything else is a constant. And so how would you take this derivative here? Right, derivative of this with respect to beta naught. Well, to make it simpler, this kind of looks like this function, right? X squared. And so, you could, if you remember chain rule, right? All you have to do is take out, first put this 2 in the front. So 2, right? And then actually, sorry, do this first. Right, 2 times, all this, beta naught minus beta 1 xi. Right, so that's the power rule, right? This 2 jumps down here and this just becomes a 1. All right, and the next thing we're gonna do is the chain rule, right? Where you have to take the derivative of the inside too, because if you look in here, right, b naught is not by itself, right? These other things are constants. We can ignore them completely, right? So you could just ignore these when taking the derivative. However, beta naught has a negative sign in front of it, and so we have to add that. When taking chain rule into consideration, we have to add that to the outside. All right, so this is the same as taking the derivative of this. Oh, well, actually, this doesn't make sense. So just this. Right, so if you take the chain rule on this, right, you first do the power rule to put this 2 in front, and then you do the chain rule and multiply the whole thing by negative. So negative 2, and you get this whole thing. And so that's essentially what we're doing here. And so here, let me erase these, right? So now we have this derivative with respect to beta naught. And so one thing that we can do is take this negative 2 and put it on the outside. Now, why is this possible? Well, if you know what the distribution rule is, well, what just distribution is in general from like algebra. You remember like 5 of x plus 3 plus x squared or whatever, right? You distribute the 5 for every single variable, right? And so then we end up with, 5x plus 15 plus 5x squared, right? And so what we're doing here is we're undistributing it, right? And so we're saying, oh, if everything's going to be a multiple of -2, then we might as well just put the -2 on the outside and divide everything by -2. So plus 3 plus x squared, right? So we're essentially going from this to this, right? And that's what we're doing here when we put the -2 on the outside. And so that's why it's mathematically equivalent. And so now we have, this expression for, the partial derivative with respect to beta naught. And we could do the same thing with respect to beta 1, right? Equals 1. Except this time, so yi minus beta naught minus beta 1 xi, right? This time, we're not just, the chain rule is a little bit more complicated. So we still do the same power rule as before. So we put this 2 out in front, right? But here, now since we're taking it with respect to beta 1 instead of beta naught, right? So let's just ignore these other two. Right? You can see that beta 1 has xi in front of it. And remember, since we're taking with respect to this, you consider xi constant. And so now, instead of multiplying the outside by just -1 to account for this negative, now we need to multiply by -xi for chain rule. So -xi here. And, just to simplify things, we're just going to put it only as xi and put the negative out in front. Okay. And so now you can see what the partial derivative of our error function is for both of these variables, right? And so if you take in calculus 1, then you probably remember something about finding the local or finding maxima and minima, right? And so, like for example, if you have a function, x squared, right? X squared, right? And the way you'd find the minima for that is setting the derivative of x squared equal to 0, right? The tangent line equals 0. So then, the derivative of x squared is 2x equals 0. So then, at what point is 2x equals 0? Oh, x equals 0, right? And you know that the minima is at x equals 0. Well, we can apply that same concept here, except with respect to each variable instead of the whole thing. So what we do now is we set each of these to 0. 0 equals 0, right? And what we're saying is that we want to be able to optimize our error with respect to beta naught and beta 1 to 0. And so this would essentially be finding the minimum for epsilon with respect to each of these two variables. And this is what we want, right? We're finding the minimum with respect to each of these two variables to minimize our error function and find a line of best fit. And so what's the next step here? So now what we want to do is, let me do 2 more equations, right? So here, let me do 2 more equations. And I labeled these last ones 1 and 0. Right, because these are going to correspond to our next. Sorry, not 1 and 0, 1 and 2. These are going to correspond to our next 1 and 2 equations. So our first 1 equation. So what we're going to be doing first here is, well, first, let me rewrite this here. Let me copy this down. Okay, so first thing we can do is we can divide both sides by -2. Okay, so 0 divided by -2 is 0. This divided by -2 is this, right? Just get rid of that -2. Now what we're going to do is we're going to split each term apart. So now instead of just getting the sum of this whole thing, we're going to have the sum of this one. Oh, well, I'm just going to omit these two just for the sake of brevity. Just writing it down faster. Of yi I minus beta naught minus beta 1 xi, right? And this is just splitting this this sum apart, right? And these you can do this on these summations, right? You're allowed to do this because they're linear. So now we have this equation, right? It's the same thing, but just split apart now. And so now, if you remember, this is a sum from I equals 1 to n. And so for this beta naught term, right, what is that equal to? Well, if we're going to do, from I equals 1 to n of beta naught, right, that's equal to beta naught for I equals 1. And then for I equals 2, again, beta naught. For I equals 3, beta naught, blah, 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 beta naught. And we're essentially adding this to itself n times. Equals 1, I equals 2, equals 3, I equals n, right? And so since this term is not reliant on I at all, right, it's just going to stay constant through the whole thing, and it's just going to be added n times. So that means that we can simplify this to be equal to n times beta naught. And so that's what we're going to replace here at the top. So instead of the sum, we're just going to replace it with n beta naught. Okay? And then here, again, like I said before, you can undistribute constants from the summation, right? We can't take xi out, right? This would be wrong because our xi is dependent on the I value, right? X of 1 is not equal to x of 5. Right, but a beta 1, that is a constant, right? It's not dependent on the I value. So we can take it out in front and, undistribute it out here. And so that's what we're essentially doing here. And so this is our final equation 1, part 2, right? And so now we're going to do the same thing with the second equation, right? And so now we're going to copy this. Right, delete this -2 because we could just remove that because both sides are equal to 0. And then, however, this is a little more complicated because remember, it gets each term in here gets multiplied by x of I. Right. So now what we're going to do is we're going to distribute this x of I. So now we have yi xi minus beta naught xi minus beta naught xi minus beta 1 xi, except there's already an xi here, so it's xi squared equals 0. And we're going to do the same thing as we did up here by breaking it up. So now we're going to have sum of yi xi minus beta naught. But remember here, before we could just do n beta naught, but now we can't because we have an xi term here, and that is dependent on I. So beta naught xi. And so we're just getting the sum of this whole thing and then undistributing the beta naught out here. And then minus, again, we're undistributing beta 1 of xi squared. And yeah, so this is equivalent to everything that we wrote before on part 2, right? All equal to 0. okay? And so if you remember, our first one is for optimizing our beta naught. Our second is for optimizing beta 1. So the next thing we want to do, I'm going to introduce a new notation here. So this x bar, this is equal to the average of x, of all the x values. And so how do you get the average of a set of values? Well, you just add them all up and you divide by however many values there are, right? So x1 plus x2 plus dot 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 plus xn all over n, right? And this is equivalent to sum from I equals 1 to n of xi over n, right? This is the same thing, right? This is just adding up all the xi terms of x1, x2, x3, all the way up to xn, and then dividing by n, right? And so I'm going to keep this here for later because you're going to need to remember this. And so it's average term, x bar, right? And just remember, oh, whoops, that's kind of cut off. Just remember, we have the same notation for y bar, right? The average of all the y values is just, this except with yi over n, okay? And so now, what we want to do is write 1 again, right? We're continuing along this chain of 2 equations. One is, I'm going to copy this down here. Okay, so we have the sum of all the yi terms, right? But if you remember here, right, let me just rewrite this for y bar, yi over n, right? Here, what you can do with this equation is you can multiply both sides by n. And so you get y bar n is equal to the sum of all the y values, right? And so that's what we're going to do here. We're going to substitute the sum of all the y values for y bar n, okay? So now instead of this, we have n y bar. And then we're just going to keep this n beta 0. And we're going to do the same thing for the x values here, right? So x bar is equal to sum of the x values. So, we have this. This is equal to x bar n. So we can write n x bar, right? And now why did we do this? Well, if you notice, every term here has an n in it. So what if we just divide by n? Right, you just delete every n. Right, 0 divided by n is still 0. So that means you could essentially just delete all these values. And we get left with this equation. And now let's do the same thing for equation 2. So, actually, we're only going to be doing it to this one in particular, right? Only this one right here. Because, this we can replace these sum of yi's, sum of xi's with x bar, but this isn't this isn't yi or xi, it's yi times xi, and we don't have an equation for that. So we're only going to be replacing this one here. So this one is equal to n of x bar. Okay. And so now, we have these equations. So what are these useful for? Well, if you notice now for the top equation for number 1, we have an expression in terms of, y bar, beta naught, beta 1, and x bar. So let's rewrite it in terms of beta naught. So let me open up a new paint here. All right, so let me copy this over. All right, we're just going to do simple algebraic manipulations here, right? So, subtract y bar from both sides. right? Multiply everything by -1, right? And then subtract beta 1 x bar from both sides. Right, and then this is what we get left with. Beta naught is equal to the y bar minus beta 1 x bar. So what this is saying is our y-intercept of our line of best fit is equal to the average of all the y values minus our slope times the average of all the x values. Okay? And so now let's bring in our equation 2. So we have this expression, if you remember. So now we're going to substitute our beta naught in here with the beta naught we calculated here. So now let's move this out, copy this. Actually, I'll just rewrite it. We have y bar minus beta 1 x bar times x times n times x bar, right? So now now what do we have here? Well, through some simple algebraic manipulations, we can actually express everything in terms of beta 1. Right, so let me simply express this all out. So we have of y1 x1 minus y bar and x bar, and then they have double minuses, so they become plus y bar. Oh, sorry, that's the wrong one. Beta 1 x bar squared, and then minus beta 1 of the sum of xi squared. All right, equals 0. So now I'm just gonna move. I'm gonna move all the beta 1 terms on the right side, and so this becomes. Oh, I can't move that over that easily. Moving these beta 1 on the right side, right? And since we moved it over, we need to negate it, right? And now we just put it in parentheses. So now we have beta 1 of, we'll put this one in first, just to make it easier to write, xi squared minus x bar squared, right? This is the same thing. If you distribute it out, you get the same thing as up here, right? And then this stays the same, right? And so the last step we have is just to divide both sides by this. So now we move this here. And now finally we have our equations for beta, our beta 1 and our beta naught. Our beta 1 is equal to this. Our beta naught is equal to this expression of beta 1, right? So yeah, these are the formulas for how to actually perform ordinary least squares. I don't know if we have time to set up our environments. Would you guys rather spend, because this is gonna, if we set up all the environments and stuff and have you guys code it yourselves, we're gonna be get pretty late into the night, like probably like 8:30 or so we might leave. So would you guys rather do that, or would you rather just me show it on my screen and just walk through the code? I forget n on the third term. Let me see. Oh yeah, I did. That was my bad. Yeah, so I forgot to distribute out this n. So this should be n. Wait, let me see. Yeah, it should be this one. Sorry. So let me move this over a bit. N beta 1, x bar, right? And then the result of that is in our final equation. I forgot an n term here, right? This is our final equation. There you go. Yeah, this should be correct. And so, yeah, what do you think, Kaushik? Do you think should we go spend the time to set up all the environments, or do you want me to just walk through it on my side?
Um, Maybe I think even if you did walk it through on your side, how long would it take? Like 5 to 10 minutes, probably.
It
Like,
wouldn't take long, to be honest, because it's just like implementing all the math equations,
mm,
just the final equations.
okay, probably. You just show it on your computer, and then maybe we can set it out like a doc or something with instructions on setting up the environment.
Yeah. Let me, we can do that next time when we talk about regularization. Oh. Hold on. Oh, it started up here. I guess my desktop. Here. Here you go. Okay. So yeah, can you see my screen? Okay. Yeah, so we're essentially going to be implementing all the math that we talked about earlier. So this we're going to be going through cell by cell. So this first cell is just importing all the libraries and stuff. It's not too important. NumPy is for matrix math. This matplotlib is for plotting our stuff, so you can see what it looks like. Pandas is for implementing data frames, so you can see it's just to make it easier to work with, right? And so now I have this data set train.csv. I think it's here. Yeah, this one. All right, let me open it with just Notepad real quick. All right, this data set is it's just x and y values, right? A bunch of them, and it's a dummy data set, right? It's only meant to show, only meant for like as a display to show ordinary least squares, right? So here we're just reading in the data set, read CSV, printing the shape, so like how many rows and columns. We're looking at the first few rows here, and this is actually a form of imputation. All right, so if you remember when we talked about imputation, that's what we, actually no, this isn't imputation, sorry. This is what like dealing with missing values. All right, and so we talked about we could drop rows, drop columns, or you could impute. In our case, we're just gonna be dropping the rows because there's only like one missing value here, so it doesn't really matter if we're missing like one row out of like, I don't know, like 200. All right, so here, all right, you can see our data set shape is 700 rows, 2 columns. All right, and then after, if we do another print afterwards, after we drop, we can see it dropped 1 row from here, right? Now we have 699 rows. All right, and so now this is initializing our like our x and our y vectors. Remember, like we were denoting it xi, yi. Right, so that's how we're starting. We're initializing it. This is essentially just plotting like what our current data looks like. So if I put that, this is the data, right? And you can see it's pretty simple. It's like literally a y equals x relation, right? Like x equals 60, y equals 60, x blah, 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 you know? It's a pretty simple line, right? And so this is where we actually implement the math. And so if I pull up the final equation here, all right, let me make this a bit smaller. All right, so if you remember, we used y bar and x bar, right? So we're just getting those now, right? Just np.mean is just getting the mean of all the x values, which is this x bar term, right? Same thing for y, that would be the y bar term, right? And then we're also getting our n, right? So you can use it in the beta 1 equation, right? And so now we're actually doing the formula here. So for I in range n, right, this is essentially implementing the sum operator here, right? So for I to n, right, what we're saying is that our numerator, we're adding xi plus times yi, right? That's what we have. Whoops. That's what we have here, right? We're adding up all the yi times xi, right? So we're just gonna go through all that. Y1 times x1, y2 times x2, add them all up to our numerator, right? And now we're gonna go to our denominator and do the same thing here. So I can actually remove this parentheses. Right, we're just adding up all the xi terms squared, right? So xi squared, so x1 squared plus x2 squared plus x3 squared, blah, 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 right? So that's what we're doing here, right? We're calculating these two summations, this one and this one, right? And then after we're done with calculating these two sums, we implement these final two terms, right? So this is numerator minus n, which is our first term here, times x bar times y bar, right, from our math equation. Same thing for the bottom, right? We have minus n times x bar squared, right? And that's what we have here. This is x bar squared. Right, so now we have our numerator and denominator. We just calculated beta 1 by doing numerator over denominator. And then our beta 0, we plug the beta 1 into this equation, right? So we have y bar, so y mean here, minus beta 1, which we calculated here, times x bar. And so that's, we're calculating both the beta 1 and beta 0 values. And so, this is what we get in the end, right? And as you can see, our beta 1, which is our slope, right? We said how the value, or the line of best fit should be something like y equals x, right? Because, at x is 100, y is 100, and it's all linear. You can see that here because the slope is almost 1. It's very close to 1. Right? What that's saying is that, our line of best fit is very close to y equals x. Right? And here we can see, our y-intercept is very close to 0. Right? And so now, this is after calculating our beta 1 and our beta naught values. Now this is just, this is all just stuff to be able to basically make it to visualize our graph, right? And after we do so, this is what it looks like. Right, so this is our final model. Right, so yeah, like I said, this is all just to make it look pretty. But yeah, this is it basically. This is linear regression data point, and this is what the line of best fit came up as, right? And yeah, I think that's all for OLS and for the code sample. Yeah, next time we'll work on setting up Anaconda and Jupyter Notebook, and so you can be able to write all this stuff yourself. Is there anything else, Kaushik?
No, I think that's it. Anyone have any questions?
Yeah, that was a lot of. I would honestly, I wouldn't be surprised if some of you were confused or anything or something and didn't understand it completely. So yeah, you can just ask me questions later on Messenger or something, or ask them now if you have any questions about any of the math behind it or any of this code. But yeah, if not, I think we're done for today.
The recording's also going to be out there, so you can just rewatch it if you want to follow the process again.
Yeah.
Thanks for coming.
Yeah, thank you.
That was pretty in-depth.
Yeah, that was super complex.
It's epic. Did you understand it all?
I joined and I was like, what the hell? This is not math. Why are there partial differential equations on my screen?
I kind of got like the gist of it, but yeah.
Wait,
I
we're still
understood it, but I feel like that was probably way over the heads of a lot of people.
Yeah.
Maybe I'm wrong.
Henry, end the recording.
Oh yeah.
Are we gonna start putting them on YouTube?
Oh yeah, we probably should.
Okay, guys, say
But
goodbye
this
because
sound
the
like
recording is
correct.
ending.
Okay,
Bye bye.